Hello again. Today we're going to be looking at an optimization problem where we're going to be minimizing the amount of material used in creating a can. And so we know that the can holds a volume of 16 pi cubic inches, and we're going to set that equal to the formula for the volume of a cylinder. We're going to solve that for one of our variables. In this case, we solve for h. So we get h is equal to 16 over r squared. We're going to then fill in the surface area of the cylinder, and we're going to replace all of our h's with 16 over r squared. Now we have a equation that represents the surface area of the cylinder, and we're going to take the derivative of that. So the derivative of the cylinder area is going to be 4 pi r plus 32 pi times -1 times r to the -2. And we're just going to want to simplify that as much as we can. So we can take a 4 pi out by factoring, and we'll be left with r minus 8 times r to the -2. We're going to set that equal to 0 because that is the process for optimizing. The reason we set it equal to 0 is because we're looking for the area where the slope is 0, which will correspond to a peak or a valley on the actual graph of our function. So here we're using the zero product rule to identify the zeros of the function. So we find two zeros for our equation, r equals 2 and r equals 0. 0 is discarded because it does not produce a solution that exists. So we plug in 2 and we get h equals 16 over 2 squared, or h equals 16 over 4, which is 4. So our optimized cylinder size has a radius of 2 inches and a height of 4 inches. The next problem we're going to look at involves finding the area enclosed by two curves. So we have functions y equals 2x plus 3 and y equals x squared. What we're going to want to do here is find the upper and lower limits of the function that we're going to be integrating. So we have to set the two functions equal to each other. So we set 2x plus 3 equal to x squared, and we move all terms to one side of the equation, leaving 0 on the other side. At this point, we factor the equation as a normal quadratic. And when we factor our equation, we have parenthesis x plus 1 times parenthesis x minus 3 equal to 0. So that will give us our two zeros of the function, -1 and 3, which will also be our limits for the x bounds. So we're going to integrate f of x minus g of x dx because we have our limits in terms of x. And our lower bound is going to be -1, and our upper bound is going to be 3. So now we integrate 2x plus 3 minus x squared so we can take the 2 out of the integral, and we can separate x and 3. So we now have 3 separate integrals that we're going to be integrating, and they all have the same limits of integration, -1 to 3. So the integral of 2x is going to be 2 times x to the 1 plus 1 over 1 plus 1. From -1 to 3, it's going to be evaluated at. The integral of 3 is 3x, also evaluated from -1 to 3. And the integral of negative x squared is x to the 2 plus 1 over 2 plus 1. Again, evaluated from negative 1 to 3. So now we want to simplify some of these expressions. So we have 2 over 2, which is going to simplify, so we just have x squared from negative 1 to 3. We can't simplify 3x, but we can simplify x to the 3 over 3. Now we want to plug our limits into the x's. So we have 3 squared minus negative 1 squared is our first group of terms. We're going to add that to 3 times 3 minus 3 times negative 1. Now, in this case, the parentheses are really helpful to keep the negative 1 separate from the minus sign. And we have 3 cubed over 3 minus negative 1 cubed over 3. So we can replace that with 9 minus 1 plus 9 plus 3 minus 27 over 3 minus negative 1 over 3. So double negative gives us a plus. And we can rewrite this as 8 plus 12 minus 28 over 3. Eight plus 12 is 20. And we can give them a common denominator of 3. So 60 over 3 minus 28 over 3 is 32 over 3. And that's all you have to do to find the area between these two curves. Thanks for watching. Have a great day.